Calculus 3 video lecture number 9 on arc length and curvature. Now you've calculated the arc length of curves in the past, curves in a plane, and for a parameterized curve, or a curve that we have a parametric representation for, it was shown that the arc length was given by the definite integral from a to b of the square root of dx dt squared plus dy dt squared dt. Now, we want to see how this would relate, or how we can compute the arc length for our vector-valued functions that we've recently begun studying. So remember, our vector-valued function we called r of t, and it had components which were real-valued functions, f of t, g of t, h of t. And in the previous lesson, we considered how to take the derivative, and remember, the derivative, r prime of t, was found just by taking the derivative of each of the components, f prime, g prime, and h prime. So as you might suspect, this definition for computing arc length extends naturally to 3 dimensions as follows. So the arc length of some space curve defined by the vector value function r of t is given by the definite integral from a to b of the square root of dx dt squared plus dy dt squared plus dz dt squared dt. Or another way that we could write this, if we're calling each of the components f, g, and h, the arc length would be the definite integral from a to b of f prime of t squared plus g prime of t squared plus h prime of t squared dt. And interestingly, the integrand, or the expression that we're integrating, is equal to the magnitude of r prime. So another way that we can think of this is that the arc length is equal to the definite integral from a to b of the magnitude of r prime of t dt. Now let's think about what arc length is exactly. Remember, this integral tells us that we're summing up a bunch of small little increments, pieces of arc length. So we're going to call each little small incremental change in arc length ds, and that would equal the magnitude of r prime of t dt. We're going to refer to this throughout the rest of the course several times when it becomes relevant again. So let's just see how to apply the definition directly using the integral. So find the arc length of r of t with the following components: 12t, 8t to the 3 halves, and 3t squared for t between 0 and 1. So the first thing we need to do is figure out what r prime of t is and then compute its magnitude. And I like to do all of that before I begin integrating because it's basically just a lot of straightforward computation. So let's go ahead, r prime of t. Remember, I'm just going to differentiate each of the components. So first component's derivative is going to be 12. 8 times 3 halves is going to be 12. And then now I have t to the 1 half. And then derivative of 3t squared is 6t. Okay, I'm going to have to take the magnitude of this vector, right? Because remember we said that the integrand was equal to the magnitude of r prime of t. Same thing as taking the square root of the sum of all of the squares of the components. And it would be a lot easier if I factored out a 6 from all of the terms. So I have 6 times 2, 2t to the 1 half, and t. Okay, good. So now that means the magnitude of r prime of t is going to equal 6. Remember, that constant's just going to come along for the ride, times the square root of, I'm going to square the first component, so 4, plus, I'm going to square 2t to the 1 half, that's going to make it 4t, plus, and then square the last component, it's t squared. And then I want to see if I can clean this up a little bit. So I have 6 times the square root of t plus 2 quantity squared, which is 6 times the absolute value of t plus 2. But since I'm given t is on the interval from 0 to 1, then I don't need to worry about using absolute value bars. I know that that quantity is always going to be positive. So I just have 6 times t plus 2. But make sure you consider it because technically that is the absolute value of t plus 2. Okay, so now we're ready to integrate. So this means that the arc length is going to be equal to the definite integral from 0 to 1 of 6 times t plus 2 dt. And then I'm going to take the 6 out and start anti-differentiating. So antiderivative of t, that's going to be t squared over 2, plus I'm going to have 2t evaluated from 0 to 1. And then this is going to be 6 times 1/2 plus 2 minus 0. So that's 6 times 5/2, which is going to give me 15. Okay. Now, you should also recall that curves can be parameterized in a variety of ways. So if we don't have a parametric representation for a curve, say I'm just given a function, we can do this in a variety of ways. There's not only one unique parameterization. For example, say I'm looking at the parabola y equals x squared, and I only want the portion with x greater than or equal to 0. So I'll just sketch that part out for you. I basically want the right half of this parabola. So here's the y-axis, here's the x-axis, and I only want the half of the parabola that's over here in quadrant 1. Okay? Well, there's a couple ways that you could do this. So one parameterization, you just start off by saying I'm going to let x equal t, and then since y is equal to x squared, that would mean y is equal to t squared. So you could write a vector valued function, r of t, with the first component t, second component t squared, and then you would have to add in the domain restriction or the restriction on the parameter that t had to be greater than or equal to 0 since we only want the right half of the parabola. However, if I wrote the parameterization as follows, say I let x equal the square root of t, then y, which is equal to x squared, would just be t. And in that case, I would write r of t with components rad t and t. And then in this case, I wouldn't need to specify that t has to be greater than or equal to 0. Why would it not be necessary? Because that's implied since the domain of rad t only includes values for t that are greater than or equal to 0. So you have more than one option. You could write your parameterization with rad t and t, or as t with t squared, but then you'll have to include the domain restriction or the restriction on the parameter. That way you only get the right half of the parabola. Now, as long as the chosen parameterization doesn't impose different restrictions, then it will not change the curve or its length. So if you compute the arc length using either version or either way that we've defined r of t, everything will come out the same. So arc length is independent of your parameterization. Now, interestingly, it is sometimes useful to use the arc length parameterization for a curve. That is, we want to let the arc length, which is s, be the parameter. So we're going to look at a simple example and then see how we can extend this further. So say I want to find the arc length parameterization for the circle x squared plus y squared equals k squared, where k is greater than or equal to 0. Now, we've studied in a previous lesson the most straightforward way to write a parametric representation for a circle is using sines and cosines, right? And since this is a circle whose radius is k, the easiest thing would be to just let x equal k cosine t, let y equal k sine t, and then I have to define my parameter t. Its domain is going to go from 0 to 2 pi because I want to trace out the entire circle. It's not just the upper half or one portion of it. So let's sketch out what this would look like before we start tackling the problem here. So here's x-axis, here's y-axis, and the circle has radius k. Okay, so I'll say this is k here. That's negative k down there. All right, well, right now our parameter is t. Instead, what the problem is asking me to do is use arc length s as the parameter. So how can I come up with the relationship between t and s? Well, what do we know about the arc length of a circle? We actually have a formula. So arc length of a circle is given by s is equal to r times theta. And in this particular case, since I know the radius of the circle is equal to k, s is equal to k instead of r. I can substitute that in. And I'm letting t be my parameter, but t is representing the angle, which is the same thing that typically theta represents. So we have s is equal to kt, which means t is equal to, in this particular case for the circle, s divided by k. So now I can write a new parameterization for this circle in terms of s instead of t. So I could write x is equal to k cosine. Instead of t, I'm going to substitute in s divided by k. So I have k cosine s divided by k. Y would be k sine s divided by k. And then I have to figure out what would the corresponding limits be on s. So I know t was bounded between 0 and 2 pi, right? Okay, well t is equal to s divided by k. So I have s divided by k is bounded between 0 and 2 pi, which means if I want to know what the limits are on s, multiply through by k in the inequality, and I would have s is greater than or equal to 0 and less than or equal to 2 pi k. So you have to include as well the limits for your parameter, or the interval for which it's defined. Okay. Well, we lucked out in this example because we were dealing with a circle, so we had the advantage of using the fact that s equals r theta. What if we were dealing with a less familiar, less user-friendly curve, and we didn't have such a formula to work with, and I still wanted to come up with some sort of arc length parameterization? What would I do? Well, first I'm going to define s of t. Remember, s is arc length. S is going to be a function of t as follows. It's going to be the definite integral from a up until t. So t is allowed to vary. S is a function of t. That definite integral of magnitude of r prime of u du. And we know that that gives us the arc length from a to t. So since we're letting t vary, now I would have arc length as a function of t. So it basically gives us the arc length of the curve from some starting point r of a to an arbitrary point r of t on the curve. And then this allows us to create a relationship between s and t. It's not going to be as clean as s equals kt in the previous example, but we will still be able to relate the two variables to one another and then switch to a parametric representation for the curve in terms of s instead of t. So anytime they want an arc length parameterization, they want you to write r as a function of s arc length instead of t. That's what the problem's asking for. Okay, so let's look at an example here. The way you begin is you're going to find magnitude of r prime of t. That way you could figure out the relationship between s and r. So let's get going. So r prime of t, derivative of cosine cubed. I'm going to have to use that chain rule we love so much. So I'm going to bring the 3 down in the front. I'll have cosine squared, and then when I multiply by the derivative of cosine of t, I'm going to have a negative sine t. So this is going to be negative 3 cosine squared t sine t. Derivative of sine cubed t, similarly, would be 3 sine squared t cosine t. And then derivative of cosine 2t is going to be negative 2 sine 2t. Okay, but I'm going to actually want to apply the double angle identity and replace that with negative 4 sine t cosine t, because when I go get the magnitude of r prime, I want everything to be trig functions with the argument t. I don't want to mix 2t and t in there, so I can use more Pythagorean identities to simplify. So now let's see what the magnitude of r prime of t is going to come out to be. So I'm going to have the square root of the sum of the squares of all the components. So if I square this first component here, it's going to become 9 cosine to the 4th t sine squared t, plus, now I'm going to square the next component. That's going to be 9 sine to the 4th t cosine squared t, plus, and then remember I replaced the last component using the double angle identity now with negative 4 sine t cosine t, so that's going to be plus 16 sine squared t cosine squared t. Hooray. Okay, can I factor something out from all of these terms? I sure can. I can take out a sine squared t and a cosine squared t. So let's do that. Sine squared t, cosine squared t. Now what's left over? So I'm going to have the 9, and then just cosine squared left from that first term, cosine squared t, plus, then I still have this 9, and then now I have a sine squared t left, plus, and then I took out that sine squared t, cosine squared t, so all I have left is 16. Okay. Cool, well if I have 9 cosine squared t and 9 sine squared t, that's just going to be 9, and then I have 9 plus 16 underneath the radical, so square root of 9 plus 16, that's square root of 25, which means I'm just going to have a 5 sitting out here. And then remember, the square root of sine squared t cosine squared t is the absolute value of sine t cosine t. But look at the restriction on t. T is between 0 and pi over 2. So that's in quadrant 1, and both sine and cosine are positive in quadrant 1, so I don't have to worry about keeping the absolute value bars. Everything's going to be positive. So I'm just going to be left with 5 sine of t cosine t. Okay, so that's the magnitude of r prime of t. That's sort of what I'm going to integrate. Remember, s of t, be very, very careful with your notation. So s of t is equal to the definite integral from a to t of the magnitude of r prime of u du. You have to define your integrand in terms of u, not t. You cannot have your upper limit of integration using a variable that matches the variable in the integrand. That's not well defined. Don't do that. Big no-no, you'll lose points, okay? So I'm going to write this as the integral. Now a is that lower limit, right? There's a. So it's going to go from 0 to t, and then magnitude of r prime of u, I'm basically going to use 5 sine t cosine t and replace the t's with u's. So now I have 5 sine u cosine u du. Okay, good. So now how would we anti-differentiate this? Well, you would need to make a substitution, right? And the nicest substitution would be, well, you don't want to use u because you already got a u, so like a w, or we're in Calc 3, we can just do it in our head, can't we? So you would let your variable be sine of u, and then cosine u du would get absorbed in the derivative of that variable. So basically you're just anti-differentiating some variable to the first power, so you're going to have 1/2 that variable squared. So I'm going to have 1/2 sine squared u, and then just keep the 5 there, okay? So no extra step necessary. This is 5/2 sine squared u evaluated from 0 to t. All right, good. So what does this give us? This gives us 5/2 sine squared t minus 5/2 sine squared of 0, and that's just 0. Okay, so what does that tell me now? Well, I know s is equal to, this was s, it equals this. S equals 5/2 sine squared t. But the worst part is not over, because now I have to go back to my original vector valued function r of t and replace all of the t's to be in terms of s. So how do I do that? Well, first I have to solve in a way that would make sense. So you don't want to isolate t, it's going to be a hot mess. So easiest thing is I'm going to isolate sine of t and then try to figure out what cosine of t would be and cosine of 2t would be, okay? So here I can see clearly 2/5 s is equal to sine squared t, and that means sine of t is equal to plus or minus the square root of 2/5 s. Now I know for a fact I'm going to use the positive radical. How do I know that? Because t is between 0 and 2 pi, and I'm in quadrant 1. Okay, so save that. Also, like that will get substituted in right here. for the second component. I'm just going to cube that because I already have sine t. Now I can easily find cosine of 2t for the last component because cosine of 2t is equal to 1 minus 2 sine squared t, and sine squared t is 2/5 s. So if I clean this up, this is going to give me 1 minus 4/5 s, which I could write as 5 minus 4s over 5. Okay, so second component's done, third component's done. Last one that I need is just cosine of t for the first component, and I'll just use a Pythagorean identity. So I know that cosine of t is equal to plus or minus the square root of 1 minus sine squared t. Now which one am I going to choose, the positive or the negative? Well, we're in quadrant 1, remember, so I'm going to choose the positive radical. So I'm going to have the square root of 1 minus, and then remember sine squared t is 2/5 s. So 1 minus 2/5 s. So this is going to give me the square root of 5 minus 2s over 5. Okay, so now I'm ready to write r using the parameter s instead of t. So r of s is equal to, now look here, I'm going to scroll back up. So the first component was cosine cubed t. So I'm going to take what I have for cosine of t and cube it. So that would be, get rid of the rad. Let's just write this nice and clean. 5 minus 2s over 5 to the 3/2. Yes, that's much more snazzy. Second component is sine cubed t. Okay, so I know sine of t is the square root of 2/5 s. So if I cube that, then that's 2/5 s to the 3/2. And then the last component was cosine of 2t. That one came out really nice, didn't it? 5 minus 4s over 5. So 5 minus 4s over 5 is the last component. Okay, pretty good. Now what about figuring out the bounds for s? Remember, we know t was bounded between 0 and pi over 2. How do I figure out what the corresponding limits would be for s? Well, I think the easiest place to go is probably here, where we have that s is equal to 5/2 sine squared t. So just substitute in, like the lower limit here was t equals 0, right? So if I substitute in 0 here for t, sine of 0 is 0. So the equivalent lower bound on s would be 0. And then the upper bound, this is b, pi halves, sine of pi halves is 1. So the upper bound would be 5/2 times 1, which is 5/2. And this is an essential part of full credit for a complete answer. So you need your new arc length parameterization as well as what the corresponding limits are on the parameter s. Okay, well done. Now, we're not often going to work with the actual arc length parameterization, but its existence and availability are important. And one idea that it's necessary for is curvature, which is what we're going to examine now. So just a definition, in case you've forgotten, we say that a curve C is smooth if r prime of t is never equal to the 0 vector. And previously we've defined our unit tangent vector, capital T of t, to equal r prime of t divided by the magnitude of r prime. And this unit tangent vector points in the direction of the curve. So say I have some curve here in space. Okay, and I want to look at how the unit tangent vector changes as I move along the curve. So the unit tangent, it's pointing in the direction of the curve. And I'm going to draw them all the same length. Remember, they're unit vectors. They all have length 1. And I want you to observe something as we move along this tighter portion of the curve. Notice that my unit tangent t, it changes direction more quickly when my curve C makes tight curves, or it changes direction more drastically. So when the curve has a tighter curl to it, or a tighter portion of a curve, then that unit tangent changes direction more quickly. Now the curvature of our curve C at a point is a measure, basically, of how quickly the curve changes direction at any point. That's how we define curvature. So curvature is going to be the magnitude of the rate of change of the unit tangent vector, that direction, with respect to arc length, the distance. So basically you want to think of it to yourself as how fast, curvature is a measure of how fast direction changes per unit of distance traveled. So the definition for curvature, we define curvature using the capital Greek letter kappa, and it's the magnitude of the rate of change of the unit tangent vector with respect to arc length. So magnitude of dt ds, where t is the unit tangent vector and s is the arc length parameter. Now here, for this definition, this is like the more intuitive conceptual definition for curvature, but it's a lot easier if you're asked to compute curvature to have a way to compute it using t as your parameter, because you don't want to have to go through the process of first finding an arc length parameterization just so you could find curvature, right? Wouldn't it be nice if you're given r of t, you can just, bam, go straight ahead and find the curvature. So let's see how we would do that. We know our unit tangent, if I were to take its derivative with respect to t, the parameter, I could do that by taking the derivative with respect to s, arc length, and then multiplying by ds dt. I can do this by the chain rule. And then if I want to focus in on dt ds, and I want to focus in on that portion in particular because the magnitude of that quantity is what curvature is. Okay, so if I'm going to isolate dt ds, notice it's going to be equal to dt dt. Where did I get that from? Right here. Okay, that's this divided by ds dt. Okay, and then I can write the numerator as t prime of t, derivative of the unit tangent, and ds dt, we saw that that was the magnitude of r prime of t. I told you not to forget that, because recall, at the beginning of the lesson, we talked about that small increment of arc length, ds, is equal to the magnitude of r prime of t dt. So cool, we have an alternate form or definition for curvature, kappa. So it's equal to magnitude of t prime of t divided by magnitude of r prime of t. Now be super duper careful. This is not the same as if you take t prime of t, divide it by r prime of t, and then take the magnitude. It is not the same, okay? You have to take their magnitudes separately, numerator and denominator. So watch out, okay? These are the scared eyes. Don't be a fool and fall for that error. All right, now that we have this definition, shouldn't we look at an example, see how to apply it? So exciting. So find the curvature kappa for a circle of radius a. Oh, so remember we have that parameterization. If the radius is a, I could write r of t as a cosine of t and a sine of t. And remember the definition for curvature that we're going to use is using t as a parameter. I'm not going to find the arc length parameterization. So I'll have t prime of t divided by magnitude of that, divided by magnitude of r prime of t. Okay, so let's get r prime of t. R prime of t is going to be negative a sine t, a cosine t. And magnitude of r prime of t is going to be the square root of a squared sine squared t plus a squared cosine squared t, which is just going to give me square root of a squared, which is a. All right, so that means my unit tangent t, remember, which is equal to r prime divided by magnitude of r prime, is going to equal negative a sine t, a cosine t, divided by a. So then I just get negative sine t, cosine t. Okay, but for curvature, I need t prime of t, right? So we're not done. Another derivative is needed. So t prime of t, take the derivative of that unit tangent. I'm going to get negative cosine t and negative sine t. And I need the magnitude of the derivative of t, the unit tangent. So the magnitude of t prime is 1, right? Cosine squared plus sine squared. So that means my curvature kappa, which is equal to magnitude of t prime, well, that's 1, divided by, and then what was the magnitude of r prime? It was a, 1 over a. So there's our curvature, okay? So whatever the radius of the circle is, the curvature is 1 divided by the radius. And that should make sense. They're inversely related, right? So if you have a small circle, then that means you have big curvature, right? Your unit tangent is changing direction more quickly, tighter curve. If you have a large circle, then that means you have a small curvature. Right? Like the Earth is round. Well, unless you believe otherwise, but anyhow, so the Earth is round, but because the radius is so large, we don't feel the curvature, right? We don't feel like we're walking on a curved surface most of the time. Okay, now, this formula, it looks pretty user-friendly, but believe it or not, there's times when it's still too inconvenient. So we've got another one up our sleeve. I mean, we've got so many ways to define curvature, just you keep up. So here's our alternate form for curvature. Kappa is equal to magnitude of r prime crossed with r double prime divided by magnitude of r prime cubed. And you might say, what in the world? Where did that come from? Well, we're in Calc 3. Don't you worry. I'm going to show you exactly how. We're going to derive this formula right now. So we know, I'm going to start with the fact that the unit tangent is equal to r prime divided by the magnitude of r prime, right? So if I rearrange that, then we have that r prime, so the numerator over here, I could write that as the magnitude of r prime times t, my unit tangent. And then, what did I tell you to remember about magnitude of r prime? I can replace that with ds dt, and then I have times t. So that means this is what r prime is equal to. ds dt times t, our unit tangent, is equal to r prime. Let's take a second derivative, because notice in that new formula for curvature, I have a second derivative of r. So r double prime is going to equal, well, now I got to do the product rule, right? So I'm going to have ds dt times t prime plus second derivative, so d squared s dt squared times t. All right, looks good so far. Now I want to try to match what I have in this formula for curvature. So how about I cross this vector with r prime? So I'm going to take r prime, cross it with what I have for r double prime now. Well, how did I define r prime? Well, look up above. R prime was ds dt times t. So this is going to be ds dt times t, That's r. And then I'm going to cross it with what I have for r double prime up above right here, which is ds dt times t prime plus d squared s over dt squared times t. Okay, do you remember some of your properties of the cross product? Well, we can distribute it over addition. Notice here, ds dt is not a vector quantity, right? So ds dt, when I distribute here, I'm just going to have ds dt squared times t crossed with t prime plus, I'm just distributing, okay? I'm just distributing this bad boy. Bam, bam. Plus, and then again, so I have ds dt times d squared s dt squared times t crossed with t. Okay, do you remember something pretty snazzy? We actually proved it in one of the previous lessons on the cross product that if you cross a vector with itself, you get, do you remember? You get the zero vector. So t crossed with t is actually the zero vector. So that means this whole second term, gone. Awesome. So now if I want to compute the magnitude of r prime crossed with r double prime, I just need to take the magnitude of this quantity up above. Well, ds dt squared, that's not a vector quantity, so it's just going to stay ds dt squared. And then the magnitude of t crossed with t prime, I'm going to use my theorem that I know about the cross product, and that's also going to be equal to the magnitude of t times the magnitude of t prime times sine of theta. Okay, now let's think here. I actually know a lot more than it may seem. I know that the magnitude of t, since t is the unit tangent, its magnitude is 1, right? And we also proved something earlier, recall, that if we know the magnitude of a vector is constant, then that vector and its derivative are orthogonal. And remember, we proved that using the dot product. So notice this applies in this particular case because the magnitude of t, my unit tangent, is of course a constant. It's always going to be 1. So what does that mean? That means t and t prime are orthogonal. So if t and t prime are orthogonal, what's the angle between them? It's going to be 90 degrees. So sine of 90, that's also going to be 1. So now this expression has simplified quite a bit, which means that the magnitude of r prime crossed with r double prime is going to equal ds dt squared. Well, I have 1 for magnitude of t. I don't need it. Magnitude of t prime, I don't know what that is, so I'll leave that. Magnitude of t prime, and then I know sine of theta is going to be 1 because t and t prime are orthogonal, so sine of 90 is going to be 1. All right, we're almost there. We're almost there. ds dt squared, I can go back and replace that now with magnitude r prime of t squared times magnitude of t prime. Okay, and then if I want to rearrange that, I have magnitude of t prime would be equal to magnitude of r prime crossed with r double prime, that's coming from here, divided by magnitude of r prime squared. Okay, but remember, since our curvature is equal to the magnitude of t prime divided by the magnitude of r prime of t, then I basically have this whole quantity now in the numerator here divided by another magnitude of r prime of t. So that's why you're going to end up with that r prime cubed, and then you have r prime crossed with r double prime. Boom. All right. Nice job. So that being said, hopefully you believe the formula in your heart now, and let's apply it with a clear conscience. So here we go. I've got my vector valued function r with components t, 1 plus t squared, and we're going to find the curvature. Okay, so remember we're going to use kappa equals the magnitude of r prime crossed with r double prime divided by magnitude of r prime cubed. Okay, so I need r prime, I need r double prime, I need to take their cross product. So r prime of t is going to be 1, 1, 2t. R double prime is going to be 0, 0, 2. And then now let me take the cross product of those two vectors. So r prime crossed with r double prime is going to be, let's see, 2 minus 0, so 2. Next component's going to be negative 2, and then last component 0. So the magnitude of r prime crossed with r double prime is going to be the square root of 4 plus 4 plus 0. So rad 8, which is 2 rad 2. Okay, so that's the numerator. Now what about the denominator? I need magnitude of r prime, and then I'm going to cube it. So magnitude of r prime is going to be the square root. Remember, here was my r prime, so I need the magnitude of that vector. This time it's going to be in terms of t, okay? So you'll have 1 plus 4t squared. So that's rad 2 plus 4t squared. And since I know I'm going to cube this quantity, I'm actually going to take out the rad 2, and then I have rad 1 plus 2t squared. And then notice in the denominator, right, this is going to get cubed. Well, if I cube rad 2, I get 2 rad 2. And then I'm going to have 1 plus 2t squared to the 3/2. Which means my curvature, in the numerator, I have 2 rad 2. And then in the denominator, I have 2 rad 2 times 1 plus 2t squared to the 3/2. So this cancels out. So lovely. And then I'm just left with 1 over 1 plus 2t squared to the 3/2. All right. Come back. We're very proud of this answer. Yes. Good. That's not enough, though. Don't you want another way to write curvature? I mean, what if you have a function y equals f of x, and you don't even have a parametric representation for it? Well, what would you do? Well, you could make one using the obvious parametric representation, just letting x be x, and then y would be f of x, and then your z component would be 0. And then I could actually use the previous form. So if I were to define it that way, then r prime of x would be, let's see, derivative of x is 1, then I'd have f prime of x, the last component still 0. R double prime of x would be 0, f double prime of x, 0. And then I would take their cross product, so r prime crossed with r double prime. Let's see, first component 0, second component 0. Only the last component has f double prime of x. So if I were to take the magnitude of that cross product, magnitude of r prime crossed with r double prime, I would just get absolute value of f double prime of x, right? You would take the square root of f double prime of x squared, which is just the absolute value of it. So my newest form of curvature is I have absolute value of f double prime of x over square root of 1 plus f prime of x squared cubed. Okay, that's because that is magnitude of r prime cubed, right? And here was r prime. So if I took its magnitude, I'd get 1 plus f prime of x squared. So yay! Let's summarize if you need it. Here's another form of curvature, absolute value, f double prime of x over square root 1 plus f prime of x squared cubed. Good. You're going to need to know all of them depending on how the function or curve is defined. Okay, now when you have a smooth curve, meaning derivative is never equal to the zero vector, we can find the unit tangent vector t. Next, we're interested in a vector that is orthogonal to t, but there's going to be many such vectors. We're going to select one in particular. Now, since the magnitude of t, our unit tangent is 1, that means t and t prime have to be orthogonal, which is proven on page 4 earlier. Therefore, t prime seems to be an appropriate choice, but we don't know that it's necessarily a unit vector, which we mentioned earlier when we were proving that formula for curvature. But as long as r prime of t is smooth, then I can make it a unit vector. And we call capital N of t the principal unit normal vector. So all you do to find it is you would take the derivative of t, your unit tangent, and then you would divide by its magnitude to ensure that good old N of t is also a unit vector. Okay? Cool. So we've got a unit tangent and we've got a unit normal. Now notice, if I cross t, the unit tangent, and n, the unit normal, I'm going to obtain a third vector, which is going to be orthogonal to both of them, right? We know that's the result anytime you cross two vectors, the third one's mutually orthogonal. And this vector also has a special name. It's the binormal vector b of t, and it's found by taking t crossed with n. And P.S., this binormal vector, it's super special. Not only is it orthogonal to the unit tangent as well as to the principal unit normal, but it's already a unit vector, meaning we don't have to divide by its magnitude to make sure that it's a unit vector. It already is one. Why is that the case? Well, let's see. If I were to look at the magnitude of b of t, the binormal vector, I know I find it by taking the magnitude of t crossed with n, right? But the magnitude of t crossed with n can also be found by taking the magnitude of t times the magnitude of n times sine of theta, which is the angle between them. But I know t, that's my unit tangent, so its magnitude's 1. N, that's my unit normal, so its magnitude is also 1. And t and n are orthogonal, so that means the angle between them is 90 degrees. So sine of 90 is 1, which is 1. So without any work, b of t, the binormal, is already a unit vector. Pretty cool. So let's look at an example here where I'm given a vector valued function r of t and asked to find the unit tangent, principal unit normal, and the binormal vector at 1, 0, 1. Now look at this. This is kind of interesting. They give me the point P, but they don't tell me what value of t yielded that point. So you just got to guess, and usually it's something obvious. Like you see how the first component, e to the t, and the first coordinate is 1. Makes sense, t would be 0, and then you just check that in the other two and it works. Okay, it's always going to be something obvious if they don't give it to you. 0, 1, something you could figure out. Okay, so here we go. I'm going to take r prime of t first, get my unit tangent, then I'm going to get my unit normal, then I'll cross them, then I'll have the binormal. That's the process. So r prime of t is going to be e to the t. Now I have to do the product rule here, so I'm going to have e to the t cosine t plus e to the t sine t. And then the last component is going to be Again, product rule time, so I'll have negative e to the t sine t plus e to the t cosine of t. All right. Now I need the magnitude of this vector. Why don't we factor out e to the t? It'll make life so much better. So I'll take out e to the t. Then I'm just going to have 1 cosine t plus sine t, and then cosine t minus sine t. All right, so my unit tangent t is equal to, remember, r prime divided by the magnitude of r prime. So r prime, I already have it here. I'll rewrite it though. So I have e to the t times 1 cosine t plus sine t, cosine t minus sine t. And then if I divide by the magnitude of this vector, well, remember, e to the t, that's been factored out. So when I square it and then take the square root, it's just going to still be e to the t. And then I'm going to have radical 1 plus cosine squared t plus 2 cosine t sine t. I'm squaring the second component, plus sine squared t plus, let's square that last component, cosine squared t minus 2 cosine t sine t plus sine squared t. All right. Good, we got it all. Now let's see what's going to happen here. Well, I notice 2 cosine t sine t and negative 2 cosine t sine t are going to cancel. And then here I have cosine squared, sine squared, cosine squared, sine squared. So each of those is going to give me 1, and then I have another 1. So I have rad 3 in the denominator. And then also e to the t is going to cancel. So t of t, my unit tangent, is going to be 1 over rad 3 times the vector 1 cosine t plus sine t and cosine t minus sine t. Okay, now I'm going to evaluate it at 0 since the problem asked me to specifically find the unit tangent when t is 0. And I couldn't have plugged in 0 earlier because remember, in order to take r prime, you don't want to plug in 0 too soon. Otherwise, you're just going to get the 0 vector. So t of 0 is going to be 1 over rad 3 times 1. Cosine of 0 is 1. Sine of 0 is 0. So 1. Last component's also 1. Okay, so first one's done. I've got t of 0. Beautiful. Now I need the unit normal. So remember, unit normal is equal to t prime divided by magnitude of t. So t prime, this is why I still needed to keep it as a function of t, is going to be 1 over rad 3, and then I'll take the derivative of the component. So I'll have 0, negative sine t plus cosine t, and negative sine t minus cosine t. Okay, so now I actually can plug in 0 when I'm computing n because I'm not going to take any more derivatives. So just to make life easier if you want, for magnitude, so you don't have to use so many trig identities, I can go ahead and say, all right, n of 0 is going to be t prime of 0 divided by magnitude of t prime of 0. So that's going to be 1 over rad 3 times the vector 0, 1, negative 1, divided by, and then if I take the magnitude of that vector, remember, the 1 over rad 3, nothing's going to happen. It just comes along for the ride. And then I'm going to have the magnitude of this vector down here, which is going to be 0 plus 1 plus 1. So I can cancel out the 1 over rad 3, and then this is going to give me a rad 2. So I'm just going to be left with 1 over rad 2 times 0, 1, negative 1. So that's n of 0. All right. Last thing I need is the binormal vector, but remember, I can take that by just crossing the other two. So the binormal b of 0 is equal to t of 0 crossed with n of 0. And then here's a slick thing you can do when you're taking your cross product. So don't distribute through the 1 over rad 3 and the 1 over rad 2. Keep them outside. And if you'll remember something about determinants, you can factor out a constant and multiply it by the determinant at the end. So I'm just going to have 1 over rad 6 times the vector that results from taking the cross product of just 1, 1, 1 and 0, 1, negative 1. So I'll have 1 over rad 6 times negative 2, 1, 1, and that's b of 0. Okay, and you'll be asked sometimes to find these vectors evaluated at a certain point, so plugging in something specific for t. Other times you're just going to leave them as functions of t. Okay, so be ready for whatever may come at you. You never know. Good. Now a little bit more about these vectors. T of t is tangent to the curve, right? Our unit tangent. And then n of t is orthogonal to it. And it can be thought of as pointing in the direction in which the curve is turning. And b of t is orthogonal to both of the others. Now together, the vectors n and b, the normal and the binormal vectors, determine a plane that is called the normal plane. And if you were to try to write an equation for it, what vector would you use as the normal vector? You would use t, right? Because t is mutually orthogonal to n and b. So t, my unit tangent, is the normal vector for the normal plane. Now the vectors t and n determine a plane that's called the osculating plane. And what vector would you use as the normal? Just basically the one that's not included, the one that's not used to determine the plane. So you would use b, the binormal, for the normal to write the equation. And together, these three vectors form what is called the t and b frame. Now, in the osculating plane is the osculating circle. And this is a pretty cool little circle. So if the curvature at some point P is equal to A, then the osculating circle has a radius of 1 over A. Okay? Oh, and I did want to mention something, because we know to find our vector B, right? You take T, you cross it with N, and then that gives you B, right? But say you were given two different vectors, how would you get it? Well, you could take B, cross it with T, you get N. Or you could take N, cross it with B, you get T. And then if the order's interchanged, then you would just change the sign, okay? So you don't have to necessarily only have T and N in order to find B. Any of the two you can use to find the third one using the cross product. Just fun fact to save you some trouble, perhaps. Okay, so here's an example. Last one, find the equation of the osculating circle to the parabola y equals 1/2 x squared at 0, 0. So what I'm going to do in order to find the equation of the circle is I need to find its radius. And in order to find its radius, I first need to know what the curvature is at that point. I'm going to use this fact here. And since I have a function of my oh so many definitions of curvature, I'm going to use the one that involves a function, f of x. So curvature is defined to be magnitude or absolute value of f double prime of x. So if you don't have a vector quantity, you can think of magnitude instead is going to be absolute value, okay, over the square root of 1 plus f prime squared, all of that cubed. All right, so I just need two derivatives. So y prime is going to be 1/2 times 2, so just x to the first, and then y double prime is 1. Love it. Such nice derivatives. So the curvature is going to equal, in the numerator, I'm just going to have y double prime, so 1, over square root of 1 plus y prime, which is x squared, and then all of this is cubed. And they're telling me they want the curvature. Well, I need the radius of the circle, but first I gotta find the curvature at 0, 0. So curvature at 0, 0, plugging in 0 for x, I'd have 1 over 1, which is 1. Okay, so that means the radius of the osculating circle is 1. Well, where's its center? Well, it should be obvious because that circle is going to be tangent to the parabola or intersect at 0, 0. Let me draw you a picture. So here's what's going on. So this is 1, 2, x, y. Let me make sure that's 1 also. That's negative 1. This is a half, negative 1/2. Okay, so the parabola here, it's going to go through 0, 0. If x is 1, then y is 1/2. So it's going to be here, here. So here's our parabola. And then I found out that the radius of the oscillating circle is 1. So the distance from 0, 0 to its center, which would be the radius, is equal to 1. So the center is at 0, 1. And you could think of it as the circle kind of sits inside the parabola in this way. Okay? So if I were to write the equation of this circle, then I would just have x minus 0 squared plus y minus 1 squared equals the radius squared, which means I have x squared plus y minus 1 squared is equal to 1. All right, we're done. Can you believe it? I hope you enjoyed that. One more section, and that will conclude the unit on vector valued functions.